Okay, looks like we got a few folks here already. Can anybody hear me? I guess not.
Hear you loud and clear.
Oh, you do? Okay, good. Let me turn my volume up so I can hear too. Now, guys, you're gonna have to forgive me. I'm Bob, by the way, because I'm a little, everybody's a little new at Zoom, and including I would have liked to have had a better backdrop than our shop, but that's where I am, and so you're gonna get a kind of a nuts and bolts view of what's going on today. So I guess we'll wait a few minutes. Everybody can hear me? Everybody can see me okay? I can't see you because I got the wrong glasses on. That's better. So I got, so Bob, you're the only one that looks, okay, you muted your audio. So I guess I can unmute.
I can unmute it. You're looking fine out here on the West Coast.
Okay, good, good.
Saves you a whole big plane ride to come out here.
Yeah, last time I was out was with you, actually. We had a going up and down the Oregon coast, which I kind of miss, to tell you the truth. It was kind of nice, but this works too. You know, it's a little easier on the budget, but that's the way it goes sometimes.
Well, we still get the content, and it saves you the trouble of, coming out to set these things up for you guys.
You know what I missed though? The last time if you remember, when I was out there, I think it was July, and yeah, all I can tell you is I stayed in this as a hotel right in Portland there, I guess. I took a walk one night after, either it was after one of the nights we did stuff, and I was walking along, there's like a highway along there, and they were the best wild black raspberries I ever ate in my life. We're growing all along that.
Well, they grow everywhere here in the bane of our transmitter sites in the AMs.
Yeah.
I can send you as many tons as you want.
We get them here too, but they're about half the size that you guys have. So, well,
we got a bunch of them. How many tons do you want, Bob? I was happy to send as many as you want. I got a transmitter site full of those things.
Well, we have other problems like poison ivy and that kind of stuff. I take the blackberries over poison ivy. So, all right. So how are we doing on time? I got about, what do we got? About 7 or 8 minutes to go here before we can. So I guess how does this work? If I guess I can unmute anybody if I just do. Can each, oh, I see how this works. Okay. So, so Chris, I'm going to unmute you. Say hello. Chris Hayes. I guess I tried to unmute. Oh, maybe I didn't. I unmuted the wrong guy. Sorry about that. There you go, Chris. There you're.
I was muted.
I can sort of hear you, but not really. You're a little more volume.
Oh, I'm in Los Angeles.
There you go. Okay. You're in Los Angeles. I heard that. Okay. So what I'm going to try to do here is I'm going to stick. I got a PowerPoint. I'll try to stick up. I'm going to do a little show and tell too, since we're here in the shop. I got a power meter here behind me. I want to show a little. I got some of the apps up on the computer here, which I can share the screen here in a bit. And
are you going to show us around your shop, Bob, a little bit? Turn the camera.
Well, I tell you what, I would do it, except the place is kind of like a mess. It looks like a bomb went off in it. So what you see behind me
feels like home.
It's more of the same. This is what you see behind me is kind of the audio test bench, and that's what I'm sitting in front of at the moment.
We call it a working environment.
Yeah. Well, the RF bench is next to it. It's even worse because I got stuff all apart here, but it's part of the demo. I got one of our remote controls open because we're doing some testing and a power meter connected to it. I'll show that a little bit. And, what else have I got? One of our audio switchers that I'm going to talk about. That's part of the talk today. So I'll show you how what's going on with that. And, we'll just do that. If you have, people, if you have any questions, I guess like we do a regular meeting, just stop me as I'm going along and I'll try and answer.
If they can raise their hand to attract your attention on the screen.
Yeah, it's kind of hard because you got so many. I already got like, looks like there's about a dozen people that are on screen here so far. Some have their video muted and some don't. Oh, I see Ron joined us. He's always got some smart aleck thing to say to me, but he can't. I guess he can't talk to me because he don't have his computer audio turned on. Ron is our director. Ron Kumetz. He's our director of engineering. And so, oh boy, a lot of familiar faces. There's Barry. He just. I guess I'll start this promptly at 3, or should I wait a few minutes, Bob, or what do you think?
Well, Everett is logged on, so he'll probably do the introductions.
Okay.
And stuff.
All right. Okay, good.
you know, welcome you out here and virtually.
Yeah, I'm not seeing video on everybody yet, so I guess they just got to turn themselves on and.
Well, they're just finishing up eating their lunch.
Oh.
You know?
Yeah, I think I would have paid for it. Oh, well.
Just send
next-
a bank card. We'll take care of it.
Yeah, next season, you know, we'll do, we'll get out again. Are you guys doing the mask routine there when you go out, or is it pretty much back to business as usual? Because here it's like they just opened phase 2 in our area. We're in Westchester County, New York, which is just north of New York City. So we've been under siege for 3 months now. So I think they just opened up. I saw our barber shop was open. You can tell I really need to get a haircut. I'm going to have to make an appointment, stand outside until he's ready.
Some places are requiring masks like Costco, others aren't.
Yeah.
Others, it's just, you know, politically
Keep the
correct.
distance.
If
Yeah.
you don't want, you know, evil eyes wondering why I was coughing from hay fever this spring.
Yeah. Yeah, you're better off just, not attracting attention to yourself, I suppose, at this point. And be like the rest of the sheep. Just where you can tell where I stand on the issue. All right, so looks like we got maybe about 16, 17, 18, 19. We're almost up to 20. I'm just glad all of this is working. This would be embarrassing. Technology company, we can't get it right. So if I go beyond, I got this, I sort of scheduled a meeting for like 2 hours, but I'll hang out as long as you guys want. I don't realize that most people are home and have things to do, but I'm here for as long as you want me at this point.
Now, see, Carl's fully correct. He's got his mask on.
It's the company rule.
Oh, you're okay. Yeah, I could run out. I'd be a little funny if I. Woo. We don't wear any around.
Roll-off filter.
We're not wearing any around the complex because the tape. It's just me and my wife here. So since we live with each other, and there's not much going on here anyway. It's pretty quiet. This is mostly a warehouse for a lot of things. There are some manufacturing businesses in here, and it's a mixture of a little of everything where we are. There's everything from woodworking shops to there's a guy that does wrought iron railings. There's again, a lot of delivery services and that kind of thing. But we're manufacturing electronics. As a matter of fact, I ran into a guy the other day who's got a mixing business where he does audio mixing, and he's here. So he wanted to come by and see me because he knew we did audio. And so I said, well, when all this funny stuff is over, you can come by and visit.
I'm in my office. I can actually take it off. So.
Looking good, Carl.
Thanks.
Keeping busy down there.
Oh, absolutely. Busier than ever.
I haven't talked to you since we were down there. Was it with BDI like a year ago, last summer?
Yeah, probably was. Yeah.
So Carl, it looks like you're on the beach.
Yeah, that's my. This is my Oregon Dunes office here.
Oh, pretty cool.
A lot prettier than my actual office.
Do. Okay. Looks like, oh, I see. Ron's on the phone. Hey, Ron, can you, if you can hear me, say something to me so that, no mic computer on this computer. Yeah. Okay. Well,
I'm here.
okay. Because if here's the thing, Ron is, our chief engineer, and if you have any really hard questions, I'm just going to walk off camera and let him.
Whoops, bad connection. Can't hear you.
Yeah. Oh, yeah. He does that a lot to me too. All right, so who are we waiting for to start this?
Probably Everett, you know.
Okay,
I invited you out, but he's the, he has to wave the flag to start this all off.
okay.
He's there, but I don't know, maybe he's away from the computer, as they say at work.
Yeah, the other thing a little tough about doing the tour here is that I'd have to walk around with my laptop. I'm using the camera on my laptop, and it's a little bulky to. I suppose I could walk around with it, but you don't really want to see the inside. But we make nice shiny things like that. So, you know, that's our 3 1/8 inch, by the way. Needed. And I got some other goodies here I wanted to show up. Okay, see, Ken, he's on. He's the guy who set me up on all this stuff. You can blame him if it doesn't come out well.
You'll have to try really hard to screw this up.
Yeah, well, guess what? You ain't seen nothing yet. Is there anybody else from the chapter who can kind of start this in case Everett got called away or?
Technically, that would be Phil.
Okay.
I haven't seen Phil Kane check in yet, so.
Phil
I
Kane
see him.
has
There
arrived.
he is.
There he is. Okay.
Phil Kane has been arrived for a while.
Yeah.
He's been muted.
Very good. Very good.
Okay. SBE Chapter 124 is hereby in session.
And 76 and 141.
There you go. There's no sense taking roll because those that are here, and those that aren't here. So the time has come, Bob. So anytime you're ready.
Okay. All right. I can get started. Well, I'm gonna do the screen share thing here in a minute, but before I do that, I just figured since I know some of you, I don't know all of you, so let me just introduce myself. I'm going to tell you a little bit I'll tell you a little bit about us. I'll introduce Ron, who's on the phone. You can't see his wonderful face today. I think he did that on purpose. So Ron is Director of Engineering for BDI. I'm the President and CEO, the owner of the company. And, it's interesting. I just tell you a real quick story. Company started in 1985. We, as a matter of fact, I talked to my former business partner just this morning. I started this company with a fellow named Frank Bergert, and Frank and I designed the very first products that we ever made. And I actually have one behind me here, which is this guy. Does anybody have any idea what this might be used for? A little quiz. Does it look familiar? Maybe not. Okay. This is the first thing we ever made, which was a program amplifier for a Gates Executive audio console. We made this, and we made a plug-in microphone preamp to go with it. This is the program amplifier, the old snowplows. This one, this one here, I got 2 of them. And Frank actually sent these to me. He had them. This one's marked prototype. This was the first one we ever built in 1985. And these were in an audio console up until about 3 years ago at a radio station out on Long Island, one of the first customers for these. And they were still using them after it was almost 30 years. So this is where we started. And where we are today is doing this kind of thing, which some of you know about our power meters. But we've gone really full really around the block here on a lot of different product categories. We started out primarily as an audio company back in the 80s and stayed that way until sometime in the early 2000s when Tom Silliman from ERI came to me one day and said, look, we need some help with an antenna monitor system. Can you help us? And that started us on this journey of building RMS power meters and antenna monitor systems, motorized switch controllers, and now we're doing a remote control. So I'm going to get into all of that, but that's kind of where we came from. We've been around, as I say, privately held since 1985, and we're poised for the future. And some of you guys are customers, and the other ones that aren't, we're going to make customers out of you after today, we hope. So let me go ahead and I'm going to screen share here. And I got a bunch of stuff that's up and running here. So let me start with the PowerPoint. Now, I'm going to start that, and then I may deviate from the end here. Let me just get that going. Okay, can everybody see the slideshow? Yes? Okay, good. All right, so the title of this thing, a long one, some things to consider for transmitter site planning, power measurement, SNMP, and multiplex over AES. And I've been doing this one for a little while, so if there are slides in here that that say hello to other chapters, you'll know why. So some basic topics I want to talk about today are I'm going to talk about RF power. I'm not going to really go through how our meters work today, although if anybody has any questions, certainly, ask a question about it. But I really want to focus in on one aspect of power measurement, and that's accuracy, or actually maximum error is what we're going to discuss. So I want to talk about how our specification comes to be, how we derive the specification for that. Next, I'm going to do a very brief tutorial on simple network management protocol. I may ask Ron to help me with that because I'm not the biggest expert on SNMP, but it is something that we dove into a few years ago, and all of our products now, all of our web-enabled products are SNMP capable. They're all agents at this point. So if you haven't been dealing with SNMP, which I kind of doubt that you haven't at this point, but if you haven't, you are going to be dealing with it if you're building any kind of a transmission facility in the near future. And then the last thing I really want to cover, which is one of my favorites, is, again, it's an audio topic, is multiplex over AES and some things to consider. Multiplex over AES is a new digital AES format to be able to feed composite FM stereo audio into an exciter in the digital domain. And there are some things that you need to really consider very carefully when implementing it. Now, we don't make any generators, at least not a stereo generator, not yet anyway. But there are things you need to do and understand about managing the signals, cabling, termination, that kind of thing. That's what I'm gonna focus in on. So, okay, so let's get started. Power measurement accuracy, the real story. And I created this triangle, and I apologize for it maybe being a little small, so I'll tell you what the little things say up in the upper triangle here, and we'll go from there. When we derive an accuracy standard for most anything in the United States, we rely on that little triangle up at the top, the NIST, National Institutes of Standards and Technology, and they have standards for most anything that you want to measure, whether it's a thermometer or a strain gauge or just about anything, including our power meters. There's a procedure, and they have a technical standard. And so, you can send just about anything you have off to NIST, pay them lots and lots of money, and they will tell you to a certain degree of error where your instrument or whatever it is that you send to them fares with their standard. And if you notice on the left-hand side of the column, there's a column of numbers here, plus and minus. And over here, there's a delta with a plus, and also a delta is the total. And as we move down the triangle, you're going to see what happens. Now, over on the left here, you see plus or minus 1%. What that means is that if you send an instrument to NIST, at least in terms of RMS power measurement, and you say, calibrate my meter and tell me how accurate it is, it can only tell you that that meter is within maximum of plus or minus 1% of their own standard. And they have various methods of doing this. One of the methods they use is to take successive measurements. They'll put a bunch of directional couplers. This is typically done with power sensors, you know, the Agilent or Keysight type power sensor where you attach it to the directional coupler sample port, you make a measurement. And what they do is they take a bunch of these and they line them up and they just take measurements and they do a statistical average. And what they've determined is that you can get within about plus or minus 1%, and that's the best you'll ever do. So, okay, fine. Now, do we use a NIST standard? We do. We use a secondary standard, and there are basically two types. The first type is calorimetry, and anybody that's been involved in television probably has used calorimetry and knows how that works. It's basically, in very simple terms, it's heating water, running it through a channel, measuring the inlet and the outlet temperature, calibrating that out, and you can turn it into watts. That's as simple as that. And of course, there are issues with doing that. You know, how accurate is the thermometer? Go back to NIST. You may have a standard for that. How accurate is the flow channel in terms of the rate of flow? How accurate is the channel itself in terms of what its volume is? All those things go into what would be called an accuracy standard for that device. We don't use calorimetry. We use a second form, which is basically a calibrated RF standard. So we'll use a generator that the level of the generator has been calibrated to a NIST standard. That means it's a secondary standard. It's been compared to NIST, and it's in our laboratory, and that's what we use to calibrate every single power meter that we make. So now take a look at the left-hand column again. You'll notice there's another plus and minus 1%. Because what that means is when we calibrate a sensor that's going to be attached to a directional coupler, and as a matter of fact, here's a directional coupler. This is a 1 5/8 without the actual electronics mounted to it yet. There's the sample port that we use. What this means is that when we calibrate the sensor and then read the sensor back with the same generator signal, it's going to read within 1% of theoretical. So now we're tallying these errors up, okay, go along. Now, these are worst case errors, by the way. That's why there's a delta, plus and minus 1%. It's going to be somewhere within that window. All right, so moving on down the triangle, we're down to the, help me out, TV folks. What color is that? Because they had all these special colors, names for colors. It's a little lighter, kind of like an olive green. So the next source of error is going to be other lab test equipment and fixtures. So you may be using a secondary standard to measure your, another standard to measure your standard. Now, there's another half of the calibration standard you have to consider, and we're building a sensor, which is, pardon me for doing this, but here's the electronics package. The RF sensor is in here. There's actually two of them in here, one for forward, one for reflected. Then there's this thing, the directional coupler. Now, the directional coupler also has to be calibrated. We have to know pretty precisely what the response of that coupler is. What do you use to calibrate the coupler, to sweep the coupler? You use a thing called a network analyzer. Well, the network analyzer also has a measurement error standard. The generator that's in the analyzer and its measurement capability. And you notice that they're all coming up to about 1%. We know that if you look at the calibration standard and the accuracy standard of a typical analyzer that's used today, whether it's made by Keysight or Copper Mountain or whoever else, you're not going to get better than about 1%. Now, these errors within themselves they're not much. They're really, that's pretty good if you can get within 1%. But remember, we're adding all of these errors up because you have to take a worst case. So now we're up to about 3% error. Now, other effects. Okay, we're down to almost down to the red field of doom here, which is your transmitter site. So we have other effects such as temperature variability, handling, and long-term effects. Now, temperature variability, we've done tests on our meters over the temperature range, and we know that from about freezing up to about 150 degrees Fahrenheit, that these meters will stay within about 1% of where they read at room temperature. So, but that's another error to consider. Long-term, variability of components. You have component aging, and there's handling. You know, if you manhandle the coupler when you install it, there can be some effect on the, you know, that will affect the geometry of the inner conductor to the directional coupler sample loop. So you can have some error there. And as I said, the long-term effects are things like component drift and whatnot. But that's not bad. 1%, you know, isn't too bad. So now we're up to about 4% error. And now we get down to a field comparison. And remember, you know, when we do this, this is the classic that we get, I won't say all the time, but we get this often. I just installed a BDI meter in my line and it doesn't measure exactly the same as my transmitter. There's something wrong with your meter because my transmitter is absolutely accurate. And I'll stop the person and say, well, just wait a minute. And I'll run them through this exact same scenario and say that the meter that's in the transmitter is subject to the same error that our meter is. And if you ever had two meters that agreed with themselves, go out and buy a lottery ticket right now because you got very lucky, because they will almost never agree perfectly. And, you know, when you get down to the bottom, you're at about 5% of accuracy, you know, plus and minus 5%. So if you do the, you know, the arithmetic on this, you could potentially have a situation where the meter in the transmitter could be off in one direction and the external inline power meter, whether it's ours or anybody else's for that matter, could be off in the other direction. You could have a 10% delta, and guess what? Both those meters are still within their, you know, within their calibration standard and within specifications. Now that doesn't happen very often. It's usually a few percent. You know, the guys at Gates Air and the guys at Nautel and, you know, Comark and all these places that, you know, Roden Schwarz, by the way, are customers of ours. They actually build transmitters and they build test equipment, but they also buy our meters for their broadcast division. Everybody does a good job. Nobody's perfect. And you have multiple standards out in the field. So this is really the story on this. And this is why, you know, you can have you can have cascaded errors, and you're going to end up with, generally speaking, we see 3-4% between meters, and that's normal. So if you see that, you know, if you have something like 20% or 30%, there's something wrong. There's something very wrong. And we're not perfect. Sometimes, you know, we'll get a meter back where somebody, you know, maybe manhandled it, or it wasn't something wasn't tightened down, and, you know, we fix it and it goes back out again, and usually there's no issue. So so that's kind of the standard. Now I got more to talk about as far as directional couplers and whatnot. So let me move to the next slide here. The thing that's, as I said, you know, about half the story is the sensor and the software to run the meter and all that good stuff. But the real story happens to be the other half of the story. This is directional coupler. And you'll notice here schematically I'm showing this is a 2-port coupler. You know, this would normally be placed after your transmitter and, you know, in between the transmitter and the antenna. In this particular case, it's a 2-port. These are how they're normally made. I'm showing it schematically. They're on the opposite opposite side of the coupler. But pardon me, we have them on both. The forward and reflective ports are on the same side of the coupler. It's a balanced coupler, and you'll notice that there's a resistor here, a 50 ohm termination on each side. So typically, if you got a directional coupler from ERI or from Dielectric, and it's this style of coupler, they're going to supply it with a termination. And you need to use that termination because that's what balances the coupler and will allow any energy from the opposite port to be swamped into the load instead of going back to the sample that you're measuring. So there are really 3 types of couplers that are in use. Bidirectional, also known as a balanced coupler, that's what's schematically shown here, which I just described. The unidirectional coupler, which is a voltage sample, which is nothing more than you know, a piece of wire stuck inside of the inside of the transmission line, basically acting as an antenna. The problem with voltage samples is they have 0 directivity. It means that they will accept the signal from the forward direction and the reverse direction. And I'm going to show you here in a slide or two why that's not a good thing for certain measurements. I wouldn't even use them on a modulation monitor, to tell you the truth, because you ever want to use a mod monitor that still anybody still does AM noise measurements, you sure don't want to use a voltage sample to do an AM noise measurement. I'll show you why here in a minute. And then the next type is a compensated coupler, which is frequency compensated, which means it's basically got a flat response. The directional couplers that we use have a 6 dB per octave rise in the response to the coupler. That means that it's not flat, and the signal output is going to rise with frequency. You say, well, why would you want to use a coupler like that? Why wouldn't you use a compensated coupler? Well, we do. We use them occasionally. wideband. As a matter of fact, I have one back here. I'll show in a minute. I have it hooked up right now because I want to show our show the app that we developed for the new meter. But that's a broadband meter. It's 80 to 1,000 megahertz. That's really the only way you can do that. But the problem there is that the bidirectional coupler, the balanced style of coupler with terminations on both ports, will give you better directivity than the compensated coupler will. That's just the way they spec out, and that's the way they work out. And better directivity for broadcast applications is really where you want to go, because it's going to give you better accuracy for VSWR protection, better accuracy for making other measurements such as AM noise and that kind of thing, which I'll get into here in just a bit. Now, again, schematically shown is how we would connect our sensor up to a directional coupler. You see one port is used for the forward and reflected sample, even though it's not labeled. So this is the, can everybody see the arrow that I'm, like I'm moving the cursor around? If I point to something, yeah, okay, good. All right, so that's forward, that's reflected. Being forward is closest to where the RF is coming from. Reflected, same thing. You want to measure reflected power. Where's the closest place where the reflected power is coming from? The antenna, the load. So that's over here. But we can also supply a coupler with another port so that you can have a completely independent port, and you can do whatever you want with this port, and it will not impact, it's not going to impact the port that's connected to the meter. So you can hook your mod monitor to this, or you can hook a network analyzer or spectrum analyzer to do a mask measurement, whatever you want to do on that side. It will not impact the power meter. And by the way, we do all of this in the same line. So you notice, like on this particular coupler, we make them all the same way. This is the sample port for the power meter. Power meter hasn't been attached to this yet, but if you notice on the other side, there's a plate that's covered. But this could be turned into a, not in the field, but in other words, if we wanted to make this as a dual directional coupler, we could do that. So you'll notice that it's all on the same coupler. So you get two ports. You don't have to have a second coupler to do this. You can do it all right here with the same coupler. And the other thing is these are a standard size. So these are, this flange to flange distance is the same length as brand X and brand Y, and we all know who they are. So if you want to swap one out for the other, you can do that without having to do a lot of plumbing. All right, so I posed the question, well, so what does directivity mean to your measurements? Well, as it turns out, it means a whole lot, and I'll show you why. Now, here's a lot of words, but I just want to give you a typical example for measuring AM noise. And I got to tell you something, as a young engineer, many, many years ago, I got bitten by this bad. And it was a very smart engineer whose name I mentioned earlier, Mr. Tom Silliman, who educated me on the subject. I was trying to make an AM noise measurement on an FM station, and it was terrible. It looked awful. And it was a it was a tube transmitter. So I start cranking the transmitter, and I'm making it a little bit better, and it's not really getting any better. And what the heck is going on here? It can't be that bad. And I talked to Tom about it at one point. He had come to New York, and he says, he says, you got that connected to a voltage sample. I said, yeah. He says, well, that's no good. He says, you're seeing the reflected port contribution, and that's exactly what it was. Just think about what happens, if you have an FM signal goes up a transmission line, okay, and let's say the load's a little less than perfect, so you're going to get some reflected power back. And I'm actually illustrating this here in this verbiage, but I just want to describe what I'm talking about. So if you don't have good isolation between this forward sample and the reflected sample, the reflected power is going to add back into the forward sample. It may be 20 dB down, but here's the thing. What happens when the carrier signal is going up the load and reflecting back? Now you have a random time delay. You have a phase difference between the incident and the reflected signal. When you add those two together, you get synchronous AM modulation. Matter of fact, RCA used to make a transmitter based on that principle. How many remember the ampliphase, or it was more familiarly known as the amplifuzz transmitter, but that was the principle. They had basically two FM transmitters in quadrature that they fed into a combiner, and it created AM. Well, you're doing the same thing in a directional coupler if you don't have good isolation. So how bad is it? Well, in this example here, I don't like to read off the page, but I'm gonna have to do it because I don't remember what I wrote here. Spec for AM noise is 50 dB or better. And let's say we take a directional coupler that has a directivity of about 20 dB, and that's pretty lousy VisWar. That's probably about roughly about 1.3 to 1 or so. So 10 kilowatt forward powers in this example and an antenna return loss of 22 dB. So that means that the actual reflected power is 22 dB down from the incident, which is about 60 something watts. I can't read what it says here because everybody's faces are in the way. But the reflected signal, remember, is subject to that round trip time, which means that the phase of that signal is random to the incident signal, the 10 kilowatts. So if it's allowed to combine, this will give could return a synchronous AM noise of, and here's the example. Directivity plus the actual antenna return loss equals the AM noise contribution of the measurement system. In other words, that's the headroom that you have. So if the directivity is 20 dB and you take 20 and add it to 22, you get 42 dB. So that may lead you to conclude that the transmitter end of the transmission system is in need of tuning. But wait a minute, if you substitute a coupler with 10 dB better isolation, 30 dB of directivity, now you got a noise floor 52 dB. And that's really where you want to be. So if you can make 50 dB noise, if you can have it's no different than measuring audio when you think about it. If you have a noise meter and it can only measure 60 dB, that's its noise floor. You're trying to measure 70 dB down like a microphone preamplifier. You ain't going to do it with that meter, and that's the same. This is the same idea here. So directivity is a very, very important aspect. It's also important for VisWAR because you could be returning a higher reflective power than you think you are. Isolation is not good. All right. So anyway, that kind of concludes the RF section of this. So does anybody have any questions, comments, anything like that? Ron, I don't know if you're still listening. If you haven't gone to sleep, do you have anything that I left out you want to add? Anybody?
No, that covered it pretty well. I'm still here.
Yeah, well, that figures. I knew he'd leave me hanging by all 10 white knuckles. All right. Any other questions? Anybody? Speak up. Okay. All right. I'm going to move on to this topic called Simple Network Management Protocol, our interoperable standard, finally, for getting things to communicate with each other. And the Cat5 cables. You got to love Cat5 cables. Everybody, everybody likes Cat5 because you just plug it in and it works, right? Well, we're going to show you how that works. Oh, I'm sorry. What was that? Somebody said something. Anyway, all right, let me keep going. All right, some very basic, and again, I don't build this as being that I'm going to teach you how to use SNMP today. That's not what this is about. I want to just briefly show some of the basic topics on this and how we're kind of using it, and that's really it. So SNMP basics, there's 3 basic types, V1, V2, and V3. These are the basic standards. I think most of the world these days is V2. V1 is kind of obsolete because it does things in plain text and doesn't really have very much security. V2 is a little bit better in terms of security. V3 has encryption. We've been hearing an awful lot about, well, you better be V3, you better be V3, but we haven't really seen a lot of resistance from most of our customers about V3 and having encryption. I just think it complicates things, and I suppose when it's absolutely necessary, we'll probably do it. But for the time being, we haven't had a lot of blowback from anybody that we're skating on obsolescence here. So basically, ours is a V2 standard. That's what we use, and I just discussed kind of what these other standards are. V2 adds 64-bit counter capability and adds read-write communities, which adds some security, and then V3 adds more security with encryption. So some real basic terms, the MIB, Management Information Base. You think I never remember what MIB stands for. I have to read it every time because I don't remember, but that MIB, but it's basically stands for where all the information is. It's nothing more than a text file. Don't I really sound smart, Ron? I really sound like I know what I'm talking about.
You do. You're really killing it, Bob.
That's great. But it's basically a text file that really tells the host device where you find stuff in this agent device, which is what our products are SNMP agents. They take direction and can give status back. Basically, that's what an agent device is. A host device is able to control and query information out of a device. Now, our host is our VDI stack software that we offer with each product that we sell, basically, that's web enabled. So that acts as the host for our products, and our actual hardware, the actual stuff you put in the rack, and the meters and whatnot are agents. What am I saying here? So we have a handful of MIBs for our product line. We don't have one specifically for every product, but within our product categories, we have a MIB for our SWP line, which includes our SWP 200 switch controller, our SWP 206 antenna monitor, and our new SWP 300 remote control system. They all use the same MIB. So it's a little easier. That way you get one MIB, you sort of see where things are and how things work, and they're all in there. Now on our audio toolbox family, which is our digital and analog audio switcher router family of products, we have something like 32 different configurations of those in 3 basic product categories. The ATB300 is an audio switcher DA, and then the GPM is a router, and then DAB300 is the dual path switcher that we make for IBOC operations. Every one of those switchers works differently on the inside. The software that runs them makes them behave differently. They use the same hardware, but they perform very differently. But they all use the same MIB to operate. So once you get one MIB going with those, you can adapt them to the other units that we make. So the nice thing about a MIB is that you can not only use it with our software, but you can use it with any SNMP enabled host device, such as remote controls that are made by our friends over at Burke or Relio, or our friends up in Canada, Dabicom. There's also third-party software that acts as a host device. Roden Schwarz makes a really nice package for facility control, and so you can use software and hardware together and never have a host device in the rack that has to do anything. That's our approach, by the way. We just to stop for a second. We believe in what we call a distributed remote control. The traditional remote control, where you have this thing that everything is connected to, is kind of going away. You could, even our remote control, which I'm going to show here in a little while, is really considered to be a peripheral device, because you can connect motorized switches to it. You can connect traditional metering inputs to it. It has relay outputs. It has the status, all the stuff that you would normally have in a remote control. But it is a standalone remote control. But if you wanted to take that and plug it into a Burke, you can do it, because it's an agent device. And you don't need to have that, a box in the rack that says, oh, I'm the remote control anymore. You have these peripheral devices and you're going to control it with software. Well, that's essentially what everybody does today. So we do the same thing. So you can use a piece of software, you can connect our stuff in the rack and never have a traditional remote control. I don't consider our SWP300 really a traditional remote control. It has a lot of traditional remote control capability, but it isn't really necessarily this thing that you have to have and that talks to everything else. The software is what does that. And the best part about that is that software is flexible. It can be adapted, it can be changed, it can be improved over time. Well, once you got a piece of hardware in a rack, you're stuck with it for however long the amortization schedule on it for your company is. Anyway, a little off the track on that. So let's get back to the next thing in a MIB, which a MIB consists of what are called OID strings, or object identifiers. And it's simply an address to identify various functions and how to perform them. So I just go through this, this is the, I guess the anatomy of a MIB. You notice the first 6 digits of every MIB is pretty much the same, and you see why. If you look at what these numbers represent, ISO group that established the OID standard. Okay, so that's number 1. Number 3 is it's organization specified text. Well, all of them have to be. I mean, if you're going to specify text, you're an organization. That's what it is. And so on and so forth. So that's why the first 6 digits. Of course, the DoD's got to be in there because they established the internet. They got to get some credit. So that's why most MIBs always start off with the same 6 digits. The next group is a company identifier, and this is something that every company that establishes an SNMP presence has to have. So Ron, help me out here. I always forget this. The organization, the standard, and we did this back in like 2011 when we introduced our first SNMP product, which was the DPS 100D digital power meter. There's an organization that gave us this number, and what is that again? You remember?
It's basically a company code. Just like as part of a MAC address, part of it is related to your company. That the
Well, no.
37691 is basically just
Well, no,
our
that's
identifier.
yes, right. That's our code. But I'm trying to remember the standards organization that's what I was looking for. Is I never remember who that is. But there's like this.
It's a registry organization just for that. Let's see. The MAC addresses are somehow affiliated with IEEE, but I forget who does the MIB, the OID company identifiers.
It's a good thing we're never going to have to do this again.
You know what? I'm going to put you on mute for a second. And,
He's going to go take
you
a
can,
look. All right.
You can talk, and I actually have it sitting right here in a folder. I'll tell you
All
in a
right,
second.
I'm going to go ramble on while he goes and finds that. All right. So anyway, so that's the company identifier, as Ron mentioned. That tells you that this is the 37691 says this is a BDI OID string. So you can always identify who the culprit is that way. Now the next 6 digits are basically the meat and potatoes of what this particular OID string is going to do. And I think in this example here, I'm using, let's start off here. So number 2 is that this is our BDI registrations folder. That's where these things are kept. The next thing is the next 2 in the sequence is the BDI product categories. And you notice how this is kind of going down in a hierarchy, like, like a Windows folder thing, because that's essentially what's in the MIB. You go down, you look through these folders. And so this is BDI product categories, and we have analog, RF, and some other, I think there's about 3 or 4 categories that we have. And this particular one, this number 2 in that particular location means it's an RF product. And then the, I'm sorry, the number 1, I'm down to the 3rd one here. I'm sorry, this one is what I meant. Now that number 1 in that position, which is this guy right here, means that it's an RF product. The next digit, which is a 2, means it's in the SWP product family. So that's either an SWP 200, 206, or 300. And the next to last one is that it's this is a specific thing saying, what is the unit information? It's going to query the device and say, who are you? And that's going to come back, and it's going to give the unit identification. It'll tell you whether it's an SWP 200 or 206 or 300. And then I can't see the last thing here, but it says SWP product. The screen sharing thing's in the way, and I can't see it. But it's the actual. I can't tell, so I'm going to move on. I don't remember what that is. Okay, so anyway, that's the anatomy of a MIB, of an OID string. So essentially, that last thing is it could either be a command function, in other words, to turn something on, turn something off, that kind of thing. I'll kind of get into that here in a second. And then everybody familiar with MIB browsers at this point? Everybody's using those. Anybody not using one? You know what a MIB browser is? I highly recommend them. If you're going to get involved with SNMP and you're going to start connecting things together, download a MIB browser. You can get them for free on the internet. We always recommend the iReasoning browser. It's free, and it's from iReasoning.com, just like it sounds, iReasoning.com. They have a free one. They have an enterprise version that you can pay a little bit of money for, which I think is a little more powerful, but you don't need to pay the money if you're just looking for a browser. They're very handy for the following reason, that if you're going to start connecting devices together, and you haven't done this before, you want to isolate where the problem is. And sometimes we have problems with this stuff. It's not like all this is all plug and play. You may be sending a command off to our device from your Burke, and the Burke, it's not working. And you say, well, let's see, what's the problem? Is it on this end or is it on that end? So the browser lets you go in directly into our device, where you can actually send a command and you'll get a response back. At least you know, okay, if I send the right OID string to this thing, I'm going to get the right response back. So then you got to match that with the other device, like the Burke or the third-party software. So that's why they're very handy to have. So if you're going to run one of these, and I'm going to show you a screen for one here in just a second, you're going to get involved with these different terms here. So there's a get term, which is what it sounds like. You send a get when the SNMP manager is attempting to take information from the MIB, find out what a value of the variable is. Response is the agent sends back the response you asked for. okay? Get next is your SNMP manager sends the next message to the agent to get information from the next OID within the MIB tree. And then you can do a get bulk, which basically is going to dump everything that's in that MIB onto the screen for you and let you see every command and every status and the nomenclature for what you need to send something to get it to do something. A set command is actually sending a command. That's what it is. You're going to set something to turn something on, turn something off, do a raise, raise lower, that type of thing. And then traps, which we don't use currently. Traps are an alert sent by the SNMP agent to notify the SNMP manager when an event happens within the device. We handle that differently. We're not currently using traps. I'm not going to say we're never going to use them, but we just don't currently use them for anything. All right. So, okay. The difference between get commands and traps. A get command, when sent, asks for information based on the MIB-F or the specific request. It knows how to ask for the information by sending the specific OID string, which the equipment knows how to interpret. A trap, on the other hand, acts more like an alarm in that it will send information back to the monitor remote control when a particular event occurs. So in other words, you have to ask for it in a get command, and it'll send you back and it'll say, well, yeah, your transmitter's off. Where the trap will say, we'll come back and tell you when your transmitter went off. In other words, you have to ask for it, it'll send it. If the trap will tell you right away. It's like an alarm. That's the difference. We handle alarms differently. We don't use traps, but we do handle them. So the get command to the equipment answers from any device, and the trap sends information back to the host when the threshold is reached or an event occurs, such as a failure. So it's kind of like a timely event. When something happens, boom, I'm going to send you a response. The get, on the other hand, is you could ask, it's like doing logs. You could ask for it once an hour, and if your power is over 105%, you'll find out about it at 3 o'clock. Otherwise, you can get an alarm back that will tell you that it happened at 2:10 p.m. Again, we handle that differently in our remote control. We do give you that information, but we don't use traps to do it. Okay. So this is, again, this screen is, everybody see this okay? Hopefully, you can read everything here. The command via the MIB browser example, in this particular case, this is using the iReasoning browser, by the way. So you pick a command out of the MIB tree, and we're going to send this. This looks like it's, this is turning the transmitter on and off, RF off and on, and either our SWP200 or SWP300 remote control system. And so there's the OID string. That is the specific string to turn. And you look at you can see the digits, and you see the 37691. That's a BDI trap, and then, or BDI. I'm sorry, I've got traps on the brain. That's our company identifier, and then there's the bunch of digits after that specifically say what this thing is. The data type is it's integer. So in other words, we're going to send a number to do the control, and the values, that's kind of grayed out, so I'll read it for you. There's always an unknown 0, and then RF off. You send it a 1, that'll turn the transmitter off. If you send it a 2, it'll turn the transmitter on. So I can actually type in a 1. I can't do it here because this isn't the actual browser. This is just a screenshot. But if I type in a 1 in the value here and I hit OK, I'm going to turn the transmitter on. You can actually do it. You don't need to have anything else. You can do this from a browser. You want to be careful doing this. You want to know what you're doing, but you can do it. So that's a good way to troubleshoot. Now, on the other hand, I can't get the the third-party software to talk to this device. Well, I go in with the MIB browser and I type it in, and the device says, I'm here and I'm going to turn on the transmitter. You know that the device is working properly based on the OID string that you're supposed to send to it. But then you got to look in the other direction to see what the problem is. So this thing is a very, very good troubleshooting tool. And this screen, and I apologize, it's a little blurry, but this is basically the browser, and it's showing the tree over here. You notice this is all looks like a Windows tree here, which is basically what it is. And then these are your basic commands and sets and whatever. And this is the table. This is the MIB table here. So this is everything about the SWP300 2T, which is our remote control system. And you can go into one of these lines, click on it, and then it'll bring up that screen. And then you could actually send that command or ask for a status back. So now, how do we use SNMP? As I mentioned before, we have a piece of software that's called the BDI stack. It comes with we don't sell our software, with the product. Unlike some other companies, we support the product with software. So this is software that
Oh,
the product. It's something that you can download from our
no,
website.
it's not.
It's also supply. I'm sorry, there was a question? Heard-
Hi.
Say something. Maybe not. Okay. So that's what you see here. This is the BDI stack program. This is the stack version running the SWP 100. Oh, this is a 300 actually. It's a 2-switch controller, and you see the 2 switches, and there's the basic commands, and there's the remote control feature here with the relays and whatnot. It's all on screen. This is for one of our audio switchers. I guess that's an ATB 300, and then here's the power meter. Although you don't even need to run this, the power meter information's up here because it's connected to this controller here. So all 3 of these devices are independently sending information back and taking commands from the BDI stack software right here. There is not a remote control in sight. Yes, this is our remote control, but this could be one of our 200s. It could be another audio switcher. You could have, you know, just about anything you want here. And you can control it. So this is what we would call distributed remote control. Each one of these devices, I'm pointing to them here, and you can't see me doing that. So each one of these 3 devices is communicating via Cat5, you know, through a network or through a, you know, a virtual private network or public internet to communicate back. So there's no hard wire other than a Cat5 cable between these devices. That's it. All right, so where are we here? Okay, so as I said earlier, this shows the interoperability of BDI products with third-party stuff, and there's our competitor down there, Mr. Burke. So you can connect all these devices to a Burke. You can use the ArcTouch Plus, the autopilot software. We'd like you to use our remote control, and I think there's some distinct differences. I'm going to talk a little bit about our remote control, and I'll tell you why I think our remote control makes a lot more sense for, you know, for the budget-conscious broadcaster than some of the others that are out there. I think Burke makes a great product. They're a tough competitor. They make a great product, and I think in some applications it may actually be a better choice for larger systems. But I'll get into that in a bit. But anyway, the point is that you can use our SWP 200 motorized switch controller, our power meters, our audio toolboxes. You notice up here I got a motorized switch which is directly connected to our controller. So all of this stuff can be connected. Once you get down here, it's one Cat5 cable going into the Burke. That's it. You know, you don't have, there's no more GPIO wiring and, you know, metering and all this other stuff. It's all done through the Cat5 connection. Now, yes, we do have GPIO on these units, all of them. You can still connect to conventional remote control systems. Even our power meter still has proportional DC outputs for the old ARC16s and other remote controls you might have if you don't have, you know, internet capability at the site and you still want to get the power measurement off the meter. You can feed that into a metering input on a remote control. You certainly can still do that. So we're still supporting a lot of the legacy stuff that's out there, but we're also moving into the future with, you know, with the Cat5 connection. All right, that's all I know about SNMP. And there's a handsome guy without his glasses on, standing in almost the same spot. And this is my favorite topic to talk about at this point, which is this multiplex over AES3, which is this scope, by the way, is sitting right here beside me. I don't have it turned on at the moment, but it's off
Hey,
camera.
Bob, can I add something to SNMP discussion before you
Absolutely.
segue?
Yep. Go right.
I'd like to also add that virtually every remote control on the market these days has SNMP capabilities, whether it's Davicom or some other smaller solutions. Sure. And we're compatible with all those, as well as some of the software-only solutions, such as Mosaic, and there's a couple out there that I haven't paid too much attention to. They're much smaller, but as Bob mentioned, it's distributed remote control is becoming a much more advantageous way to pursue this. So you know, we've been very careful to maintain compatibility with everything that's out there.
Well, that's it. We think that there are places where you're going to buy an ArcTouch Plus and install that, but you're also going to buy BDI gear, okay? Because it just makes sense. Like, for example, I could see a scenario where somebody buys, specifies an ArcTouch Plus because they have a large system. It might be a directional antenna system. It may be, I don't know. I mean, maybe you just need a lot more stuff than what we can provide. However, you could still use an SWP 300, one of our remote controls, as a peripheral device because it does the motorized switch control. You can connect our meters directly to it, and then you still have control outs and status inputs and whatnot. And here's where this might be very, very important. This ends up being a backup. It's a remote control within a remote control. So if anything happens to that larger system, like the Burke or the Davicom, you still can tunnel into the SWP 300 and you can change the transmitter, main to standby. You can turn it on and off. You can control the other things. You can still monitor your power. You can still do all of that directly. So it ends up being kind of like a redundant system. I remember, 30 some odd years ago when I was a chief engineer, first station I ever walked into in New York had 2 remote control systems. And I said, what the heck is this? Oh, we have to have redundancy. Of course, the redundancy consisted of, one was a Mosley PBR 30 and the other one was a Mosley TRC 15. And they didn't, they weren't exactly redundant, but everything was in parallel. They had all these connections and everything. If it was a nightmare, but it all worked. They had 2 completely separate remote controls. That's the first time I'd ever seen anything like that. And now, certainly, you can do that a heck of a lot more easily than you would ever have been able to do back then. So the idea of redundancy, where you think you have to buy 2 of a very expensive thing, no, you could buy, and specify a larger system like a Burke or a Davicom for very, very complicated things. But I think for the most part, and again, I'm going to talk a little bit, I want to get through all this. I'm going to talk a little bit about a remote control and why I think it makes sense. I think, for the cost wise, ours is a less expensive solution. It's easier to implement in a lot of cases. And it's probably enough remote control for an awful lot of places. We started off by saying, well, for the low power guys, translators, things like that, this thing will go beyond that. It'll do, you can do a full service radio facility or even a television facility, with this remote control system and not need anything else. Anyway, so I'll come back to that in a bit, but I want to just cover this last topic, which I have fun doing. I put this together, and this is kind of neat. So multiplex over AES3, I described earlier what it is. It's basically a digital method that the processor guys got together and created a standard so that you can now send multiplex, composite FM stereo. Now, I'm not referring to the audio over IP standard to do this. I'm talking about what comes out of the processor, the transmitter site, and goes into the exciter. So this is basically, it's an AES3 standard. It runs at 192 kilohertz sampling. And, up to now, most broadcasters are familiar with 32, 44.1, and 48, and 192 kilohertz, is kind of new for broadcasters, and it's fraught with issues, which a lot of folks found out early on. And that's why we got involved in this and created this. So let's talk a little bit about what's required. So you want to do multiplex over AES, as Mr. Fields would have said to the boys, Abbott and Costello. So look at these sample rates on this chart, and there's the symbol rate and the interval rate and the system bandwidth, the first 4 columns. So, 44.1, which is pretty standard stuff, or 48, which is, pretty much used throughout in broadcast. You need about 30, and that's megahertz. Look at up top there. It says megahertz. 30 megahertz worth of bandwidth, even 48 kilohertz. Now, let's look at 192, where we now need a whopping 122.88 megahertz of bandwidth. That's RF at this point. So that's a lot of bandwidth. And why do we need all that bandwidth if all we're doing is 192 kilohertz sampling? Well, these are square waves. Square waves are made up of harmonics, lots of them. And so you need to have up to about, about the 10th harmonic here to run through the system. Otherwise, your symbol rate, it's not going to be able to resolve the clock, and you're going to have lots of problems, which some of our customers kind of found out the hard way. And this is why we got involved in this in the first place. We make a product that does 192 kilohertz sample rate, and we had some customers that bought these. It's our AES 400 series switcher that we've been kind of making for a long time. And most people buy them and they put them in typical AES-3 configurations, 44.1 or 48, and they work fine. But they're rated up to 192 kilohertz, and they do pass 192 kilohertz signal. But a lot of folks found out the hard way in a real big hurry is that you got to treat it a little bit differently than you do 44.1 audio in terms of the cable and the termination. So let's keep in mind you need 122 megahertz. So let's look at some of the cabling. It's been used over the years. Belden 8451, which is basically audio cable, and you could get away with it. You could use it for 44.1 and 48 kilohertz over short runs, and it works. You know, it's the cheater's method, but I wouldn't recommend it. But but you can do it. Now, Belden also then came up with the standard 1800F, which is digital audio cable, and it's allegedly 110 ohm impedance and all that good stuff, and it's supposed to be good for greater than 48 kilohertz. Then, of course, there's Belden 1694A, which is an HDSDI cable, otherwise known as RG6, coaxial cable with a BNC connector on it. So I'm gonna, anybody have a guess which cable I'm gonna end up recommending at the end of this? Anybody? Well, we'll leave it a secret until we're done here. All right, so tell you how we got into this. We had a customer who bought one of our AES 402 digital audio switchers. 2-input digital audio switcher, has 4 digital outs, and analog output, has a silent sensor in it. Standard product we've been making for a lot of years. And we shipped it through the distributor, and guy got it, and I don't know, got a call from the guy and said, gee, I got one of your switchers and we're having some trouble. So what's that? He said, well, here's what we're trying to do. And he described that he had a composite, a processor, and I want to leave the processor name companies out of this because it really is irrelevant to the discussion. But processor company A, that he wanted to use the new composite over AES standard, and then he had 2 processors, and he wanted to be able to switch between them to feed his exciter, and that's what he bought our AES 402 for, and it wasn't working right. So what's the problem? He says, well, your unit seems not to be passing the signal. I said, okay. I said, when I got to think about it a little bit, I said, well, all right. Let's take a look and see what goes on here. And because we hadn't seen this before. We hadn't actually have anybody who ever tried to use one of our units at 192 kilohertz. Now, I have a 192 kilohertz generator here, and we test every one of these that goes out to make sure that the light comes on. As a matter of fact, behind me here, I don't know if you guys can see this, whoop, but I have one of these plugged in right. That's one of our AES 403s. It's plugged in, and I switched it. So, the generator's turned off. But let me turn the generator back on here, and you'll see that the 192 kilohertz light, I don't know if you can see that, that's on. Okay, so it's passing 192 kilohertz, and I can tell you that it is because that tone is coming out of that unit. So we know it's passing it. And I skipped ahead here. I didn't want to do that. Okay, so let me sit back down again before I fall. So there's something up. So I said, all right, let's get processor A company and transmitter B company send me some of their product, and I'm going to put it all together on the workbench, and we're going to see what's going on because I'd never done this before. So with the help of one of our distributors, who kind of twisted the arm of one of the manufacturers, they sent us the needed equipment. As a matter of fact, I got 2 different processors. I got one from processor company A and one from processor company, and we tested them. And I got an exciter from a transmitter company up north. And I just gave it away. And put all of the stuff on the workbench, and lo and behold, it didn't work. So I said, okay, well, let's figure out what's going on here. So I started to scratch my head and say, there's something up here. I could pass 192 kilohertz tone from this same generator. This is a little digerator is what we use. I mean, it's, a good little generator. I could pass it through our unit, through the processor, through the everything, and it was coming out the other end just fine. But you go to multiplex over AES, and it wouldn't work. There's something a little bit different about that waveform. I don't know what it is. It shouldn't be because it's an AES format. Never mind any of that. When we looked at the scope, and pardon me for these scope presentations, may not be the greatest. Pardon me. The left-hand scope picture, which may be a little hard to see, but you notice there's a lot of ringing here, a lot of overshoot and undershoot here. This is 30 feet of 1800F. This is 110 ohm cable that's been terminated with 110 ohms at the scope. This is from a generator to the scope, 30 feet of cable, nothing in between, no equipment, nothing. Pardon me. And you see what happens. Now, to the right-hand picture, this one here is 30 feet of 1694A, a coaxial cable, a 75 ohm cable, with a 75 ohm termination at the scope. Now, notice, pardon me, I'm gonna go off camera here in a second to get my drink of water that I should have had. Maybe I can elicit some help from the peanut gallery. Stand by one. I'm gonna be right back. Just Ron, entertain the troops. I'll be right back.
Does anybody have any questions so far?
I could add a comment about using audio cable for AES EBU. My experience with a lot of the Neumann digital microphones that I've been using for the past 10 years, it turns out that the best cable, oops, have I been muted? No.
No, I hear you. I'm back.
The best cable that I seem to be successful with is some of the oldest Belden crap that you can imagine, things that are RF prone, whereas if you hook up a very good piece of RF proof Mogami, the AES signal won't go through 25 feet of it. So that's been my experience.
Really interesting. So, okay, so what we did here, just to continue on with what I started with here before I had my coughing fit, you see the right-hand scope picture this is coaxial cable. So now there's a bit of rounding, as you can see, but for all fairness here, the scope is 100 megahertz, an old Tektronix 2236, so it's 100 megahertz bandwidth scope. So some of that rounding has to do with the bandwidth limitation of the scope. But notice the absence of the overshoot and the apparent ringing, and there's also a lot of clock jitter, as you can tell there. So all that's gone. So okay, what's happening here? Basically, what's happening is the cable's running out of bandwidth, and this just goes back to, this is a little bit of audio 101 stuff here, but this illustrates what's happening. If you look at this waveform, this is a square wave at 100 hertz, and it's being passed through a four-pole Butterworth 1 kilohertz low pass filter. Basically, the 110 ohm cable, which I'm going to show you here in a minute, I'll show you a chart that shows the bandwidth, is acting as a low pass filter. It's essentially what's happening. So if you look at here, this is an audio representation. But the same thing, you multiply the 100 hertz up to 125 megahertz, and you get the same effect. So you see there's a square wave, and a square wave is made up of harmonics, the odd harmonics. And you'll notice that there's overshoot and undershoot. And if you really expand this out right here, you notice that this looks like a sine wave. Well, that's because it is a sine wave. What it is, if the scale here is in 2 milliseconds per division, and this is about 1/2 of those, so that's about 1 millisecond sine wave, which turns out to be 900 hertz. Well, think about this. What do you think is happening to the phase of that signal at 900 hertz if the 3 dB point is 1 kilohertz? It's rotating like mad at that point. So you have a phase rotation, and it is no longer arriving back at the scope. It's measuring this in the same time relationship than the other harmonics. That's what's causing the overshoot. It's a bandwidth limitation. Very simple. So now we look at this in the time domain versus the frequency domain. Of course, the right-hand side here is just basically showing the spectrum and the amplitude distribution of the harmonics. This would be a normal square wave. This is obviously the fundamental here at 100 hertz. You'll notice the 900 hertz sine wave, whoops, I didn't mean to do that yet, sorry. is at about 2/10 of the value of the fundamental. So that's why it's so much smaller. Actually, did I go in the wrong direction? I did. Wanted to go back one more. You notice that this is pretty small in amplitude compared to the square wave. Well, it makes sense. You see the amplitude distribution here. That kind of makes sense. So now, let's look at another filter. This waveform now, you have two waveforms. They're superimposed. One is red, and that's the Butterworth response that we looked at earlier. And now we've added a Bessel response. Now, most of you know that, I'm sure everybody knows that a Bessel response is linear phase. That means it has good step response. And it also means that all the harmonics are going to travel through the system at the same speed. So you notice the absence of any overshoot. It's kind of hard to see here because they're superimposed, but the green is very flat. There's a little slew-induced distortion here, as you can tell from the, not perfectly perpendicular here, but that is linear phase. Think coaxial cable. Coaxial cable by its nature is linear phase. And that's why in digital television, for example, we don't use waveguide anymore on a transmission system because it's very hard to control the phase. You get bunching, right, of the phase with waveguide. So we can't use it because that creates problems for digital television. So that's why coaxial cable was used. It's the same thing here. Same thing is going on. No different. Now, we took these pictures here with properly terminated. This is through everything. This is taking the processor, going through that AES 403 that was behind me here, and going to the transmitter. Now, these are two different processors, and all we did was we took 110 ohm transformers, went down to 75 ohms, ran cable, a 75 ohm cable between the processor, our switcher, which is outfitted for 75 ohms. You can order them that way. As a matter of fact, I'll show you that in a second. And then we went out to the transmitter, transformed back up to 110 ohms because the transmitter maker and the processor maker don't make a 75 ohm termination. I've suggested to all of them that they do, and only one processor company came back and said, yeah, you know, we think that's a good idea. And whether they've implemented it or not, I don't know. But so this is what you end up with in the real world here. This is through, you know, from the processor through 30 feet of cable, I think we used on this, and then we terminated it, you know, in the transmitter going through our switcher. And you notice that, sure, there's some rounding and there's a little bit of overshoot, but perfectly acceptable. And guess what? The transmitter were very happy with that. As it turns out, it was the transmitter termination that wasn't happy with the signal. Our unit was actually decoding the signal. You know, I had the customer plug in a set of headphones and say, hey, can you hear audio coming out? Now, it doesn't do the multiplex decoding because, you know, the AES transformer and the D to A converter is a standard. It's just looking for, you know, standard digital audio. And it will decode the L plus R. And sure, he heard music playing. And I said, well, then our unit's passing the signal, it's decoding it. It's just that the termination at the other end didn't like it. But once we converted everything over to coaxial cable, life was good. And I thought I had another slide here, which I don't. For some reason, it got missed. Anyway, there was a slide that showed the bandwidth consideration for 110 ohm cable. And it launches out at about 20 megahertz. It really is down quite a lot. Where the coax is only down about a dB or two at 100 megahertz, the same equivalent length of RG6. So I would say that, you know, television guys know this. Most of the television customers that we have that are buying our products that are doing digital audio will specify the 75 ohm termination. And the reason for that is simple, because that's what's running through their plant. They have 75 ohm cable everywhere. So they run, when they do run a discrete digital audio, whether it's 44.1, 48, or whatever it is, you know, they're running it through coax. So they already know this trick. But this is kind of new to radio guys. They are used to using everything with XLR cable. So, you know, anyway, so we have some recommendations. We recommend multiplex over AES. You know, management, here are the recommendations. Use coaxial cable. Don't try and use 110 ohm cable. Just don't do it. Keep the cable lengths as short as practical. Use high quality transformers like the Canary, ECJ series or equivalent. And of course, if you're going to switch and distribute, we recommend one of our AES 400 series outfitted with 75 ohm IO. So I think that is the end of the, well, no, I actually got more. I wanted to talk a little bit about a remote control system, the SWP 300 remote control system. We came out with, probably about a dozen years ago, we started building motorized RF switch controllers, the SWP 300. I bet some of you guys are on this call this afternoon probably have them. And you know, we started making actually we started private labeling them for ERI back in the day. And as a matter of fact, the very first power meters we made, we also made for ERI, as I mentioned earlier. You know, Tom Silliman had asked us to develop this product line for them, and they still buy product from us. Of course, we don't put their name on it anymore. They want us to, they want our name put on it because I don't know, we sell a lot more meters than they do, and I guess they enjoy our reputation. In the beginning, I thought it was going to be the other way around, but they seem to think it's better to have our name on it. But whatever, I mean, that's it's flattering, I have to say. But in any case, so we started building these motorized switch controllers, and then we added the power measurement integration to it. So you can take one of our DPS 100D power meters, like the one I keep showing here, this guy here, and there's a connector on here that you can connect it directly via RS-45 to the controller, and it gives you a couple of different benefits. One is that you have a rack display for the meter, you know, but it also provides automatic changeover capability. So if your transmitter goes off, the power meter says to the controller, hey, the transmitter's off, switch transmitters. It can do that automatically. It can manage the interlocks and transmitter on and off functions and does all of that. That it also protects your switch from potential burnout. If somebody jumps out an interlock with a clip lead and you go to try to move the switch with the transmitter on, and the transmitter doesn't go off, the switch won't move. So it'll wait for the RF to be removed. So that's a safety factor we've got built in. So, you know, we've been doing that for a lot of years, and it's been a very popular product. We sell a lot of them. We sell all the accessory cables for them. You can buy you know, whether you've got a Delta switch or a dielectric switch, doesn't matter, 50,000, 60,000 series, ERI, Myatt, Spinner, MCI Mega. If I left anybody out, you know, any switch manufacturer, we make an interface for it that connects directly to the rear panel of all of our controllers. And that's the only connection you make to the switch. No more having to worry about interlock paths and all that. We bring it out to 2 relays on the back of the unit. That's it. One goes to one transmitter, one goes to the other. You're done. You know, you can use interlocks, or if you want to hook up the transmitter on-off commands, you can do that as well. We even make the cables for those now. If you have you're doing a new installation, and you're either using one of our SWP 200s or one of our 300 remote controls, you can buy all the cabling that you need to interface those transmitters through the switch. And if you're using somebody else's remote control, it's a Cat5 connection, so there's no GPIO to worry about, although we do provide it. It's there. So this becomes the most plug-and-play motorized RF switch controller that you'll ever buy. And same thing with a remote control. Now, by the way, recently, one of our competitors announced that they have a revolutionary new product, an SNMP-based motorized RF switch controller. Well, I hate to tell our competitor, they'll remain nameless. Maybe some of you know who they are. They make RF switches, by the way. That they are trying to say that they were first doing an SNMP-based motorized switch controller. Well, I don't know where they've been. We've been building one for 3 years now, 3 or 4, almost 4 years now. And it was one of the very first products that we built that was SNMP capable. The company that developed it for, you know, the manufacturer that's offering this for sale, we had SNMP before they did. So just, you know, just for clarity on this, you know, we are well acquainted with SNMP, and we've been building this product for some time. So we get now to the SWP 300, which is our new remote control system. Looks very much the same as the 200. And the reason for that is it's based on the SWP 200 chassis. It's the same hardware, tried and true, tested. Everything that's in this unit, we've been building for about a dozen years now. Hardware is pretty solid. What's different is the software. You know, we've added some additional boards in the unit and provided additional control and whatnot. And in addition to that, you can buy the remote control, which could be this guy right here. And that provides you with 8 status inputs, 16 control outs, 4 analog inputs. Now that may sound like an odd combination of stuff, but when you consider that we do the transmitter control stuff, the transmitter on and off with a separate connector. You don't have to eat up raise and lowers to, to do all of that. So, but if that's not enough, we originally we envisioned this product to be for it's like the translator market and the low power market, where this is a remote control. You hook your switch up to it, you hook your transmitters up to it, a couple of other devices that you might have that you might want to control and monitor, and you're done. Cat5 connection to the outside world, and you're controlling and you're monitoring from a remote location. But then we decided to add the IOX24 panel here, which is this guy, which connects basically with a single cable to the SWP300 chassis. And that'll give you 24 additional control outs, status inputs, and 8 more analog inputs. And you can add more of these. You could add a second one if you wanted to. So this now becomes a full, basically a full-blown remote control system. And again, it's got the motorized switch control built in, so you don't have to have a separate motorized switch controller. It's built into the product, up to 2 switches that you can control with this controller. It has direct access to our meters, so no worry about C remote going into an analog input for that, or having the SNMP. You don't have to worry about any of that. It just directly connects to our unit. There's a temperature sensor that plugs into the power meter. It all reads directly out. There's no scaling, none of that stuff you have to worry about. It's all incorporated into the product. So it really becomes a real plug and play product. That's the end of the presentation, but I'm not done. Let's see here. I just want to do this. I want to escape out of this and close this. I'll get rid of that. And I stopped the sharing. Okay, well, I want to share my screen. I want to share a different screen. So let me show you what we've been working on. So let's share this. This is the new skin for the SWP300 remote control. This is brand new. And so I'm just briefly, there's a video about this on our YouTube channel, by the way, which is brand new. If you go to our website, we got some videos up there. We just got started with this. We just did a couple of different videos that are, that describe some of these products. So but I just want to just briefly talk about this. So broadcast-devices.com, up in the upper right-hand corner in YouTube, and go there and you can watch a little longer video about this stuff. But this basically is our remote control screen, and this is the main screen. Shows you the switch positions. You can add power meters in here, which I think we have one connected here and showing 0 watts. That's why you see the arrows. Interlock open, because there is, and we don't have another. There's no power meter on the other port, and I probably haven't shut it off at the control. But so you have your switch control, and like most companies remote control companies will make you write a macro for all of this stuff, like controlling a motorized switch. Well, it's incorporated in right here. It's done. You just push a button and boom, just move the other transmitter to air. So that's all done for you. There's various things that we have kind of built in that are already kind of built into the mix. Plus the fact this will do this automatically if you have it in the auto mode. Setup on this is very easy. You can go in and you can set up your analog inputs, set up your scaling, whatever you want it for, percent, voltage, current, that kind of thing. There's no test it and go to it. You have a meter that's right on screen here, and it'll take your sample and you can convert it to whatever you want. That's something we did. The GPIs, you can name them. You can set them for invert or not. GPOs, you can give them a name. You can set them for latch or momentary. Same thing with the relays. This is the setup. There's no complicated software you got to learn how to use. It's just take these tabs and look at them. There are RF meters. You can give them names. We have logging capability, just like everybody else. We have, timed events you can set up, like you could do directional antenna changeover, day, night, that kind of thing. You can set up your calendar for that, do all of that. So we pretty much have put a lot of these features that you find in the more expensive remote controls in a product that's kind of in the middle price point. Once you put one of these in, every one of them is the same. You can use the same GUI to run them, and pretty much set your sites up and look at these. It's very, very easy to do. But again, there's a little more descriptive video on the YouTube channel describes a few other things. One more thing let me just minimize this. It's probably going to make, it says I'm not sharing anymore again. So let me bring up, oh, I still am sharing. Okay, let's bring up the, here it is, the meter. This is the new skin for the DPS 100D meter. Now, we've made some significant improvements to the operation of the DPS 100D meter. This is now a Windows app. So the current product, which we're going to start delivering these pretty soon. The current product uses a browser interface, and it does use, it relies on Adobe Flash. And of course, a lot of you have probably heard about the fact that Adobe is going to end support on Flash at the end of 2020. That doesn't mean that support on Flash is ending. It just means that Adobe support for it is. And to be more specific, there's a division of Samsung that has purchased that division of Adobe, and is going to continue to support Flash and develop Flash applications. So Flash support isn't going to truly end. It's just that Adobe is going to end it. But, you know, we've heard from a lot of customers who have told us that, gee, we really would like it if you didn't rely on Flash. So we got busy and we've eliminated Flash pretty much from the product line. So now our products run on an app. And so this is the Windows app that's running on this particular laptop that I'm doing this on with you.
Except we're not seeing it.
You're not seeing, oh, I'm sorry. Maybe I got to, you're not seeing the skin of the meter? Why?
No.
Let's see why not. I don't know.
No, all you're seeing is the graphic of the switch positions and the
Oh, that's still up. Oh, okay, hold on. Let me close that. Oh, maybe I have to close that and then get rid of that. And oh, you know what? I closed the wrong thing. How about now? Well, I stopped sharing now, didn't I? Now let's let me hold on. I'll get there. Share screen, and I want to share this guy.
You're no longer killing it, Bob.
Ah, are we there now? Can you see that?
Yes.
Okay, good. All right. So anyway, so this is the new screen, main screen for the meter. This is, as I said, is a Windows app, and you might have noticed there before. You can have more than one of these running at the same time. You can name the sites and whatnot. So this is the main screen. And one of the things that we added that we're pretty excited about is that you could have always done this, but you had to call us, and it was a deal. Every one of these meters that we make now, for FM, for example, is frequency agile in the field. You'll notice the frequency comes up on the screen. It says 98.1. There's a method that you can go in and you can change the frequency, and it'll remain calibrated. So no send the meter back to us, and we charge you a lot of money to calibrate the meter. I mean, you can send the meter back to us and we'll calibrate it for you. And we will charge you a lot of money, but it's not necessary, is what I'm saying. In other words, we've had occasions where customers have bought the meter from us and have installed it and said, we just bought this other station, and I think instead of putting it here, I want to put it over at this other station, but it's on a different frequency. How do we move it? Well, there's a way to do it with the current production meter, but it takes some time to do. This you can do. It's information stored away in the meter. All the cal points are there. So that's significant. So we're doing that. We added a few other things. The old meter interface, you had to pick on the screen whether you wanted to display VSWR or reflective power. Now we can give you both simultaneously. Rest of the stuff is pretty much the same. You still have the temperatures and the pressure sensor and the set points. These are alarm points. Some of them are saying everything is clean and green. And then you got, it's saying we have the pressure set for if it goes below 5 PSI, tell me about it. And it's telling you about it because it's 0 PSI, or power is less than 9 kilowatts because it's reading 0. So yeah, these things are alarming. And of course, if you have the alarms turned on, it'll send you an email and tell you about this stuff, our GPI status. But if you notice, the previous screen that I showed, of the SWP 300, it's the same layout. It's just tabs. This is how you connect to the meter. I've got it hooked up to one of our internal things here. It comes back. And this is something too that's neat. It'll report back what the meter model number is, the firmware revision, the serial number of the meter. and now knew the directional coupler ID, the serial number of the directional coupler. Because a lot of times people call and say, gee, I got this problem, and well, I'm not at the site. Well, first of all, don't ever do that. Don't call me with a problem if you're not at the site. Please don't do that. If you want help, you got to be at the site. If you want help with the thing that's at the site, but anyway, you can actually interrogate the unit and see what the serial numbers are without actually having to be at the site. Then we got events, which is the log here. This is the alarm events. I don't have any alarms turned on, so it's not showing anything here, but this is a log of events, and you can actually have this thing email you and send you a log. This is just the power meter, by the way, it does this. I mean, the remote control will do the same thing, but oddly enough, a lot of the smaller operators, the guys that have a single transmitter or a translator operation, they'll use one of our meters as a remote control, because you can set the two relays to turn the transmitter on and off, and then you get some basic information along with the 6 general purpose inputs, which are over here. You can name them anything you want. You have these closures that you can call them whatever you want. And as I say, you can turn the transmitter on and off if I have that enabled, which I don't at the moment. So we just made this a little easier to set up. And one of the other things that we did is we changed used to be that the reflected power trip point was always reflected power, was not VSWR. And many people asked us about why that was. And it's because of, believe it or not, IBOC. If somebody buys one of our meters and puts it in, here's a real world example. In Chicago, we did a rather large master antenna system, monitor system for, as a subcontractor, ERI. And they installed a separate digital antenna and analog antenna. They wanted monitoring on both antennas. Well, the mutual coupling between the two antennas was great, as you can imagine. And so residual RF coming off of the analog antenna is feeding back into the digital antenna as being read as reflected power. It really wasn't, because it was just ingress from the other. It was incident power from the analog. Well, it was about as much power as the digital outputs of all of the transmitters of the 10.
Hello?
Yeah, yes, sorry. Somebody asked a question?
There is no Janie.
There's no what? Okay.
Mute your mic, Hal.
Okay. Oh, somebody thought their mic was turned off. So in any event, we had as much reflective power as we had forward power. So how are you going to measure VSWR that way and use that as a trip point? You can't, because you'd have an infinite VSWR. So we used reflective power. Actually, going back to Mr. Silliman there, who said to us, if you build a meter for us, this is how I want it to work. I don't want you to use VSWR. I want you to use reflective power for the trip. So we said, okay, we'll build it that way. You're the customer. We're going to build it that way. So we went off and we built meters that way for years. But then we had customers that say, oh, no, it's got to be VSWR. Because, we don't, a little secret, we don't only have broadcast customers. We have other, customers outside of the broadcast arena that are more interested in VSWR. So we changed it. So now you can set a trip point for VSWR. So that we've added that. You can still use reflected power, but you have to decide which one you want to use. Use a set point for that, and right here, you can trigger on SBSWR or not. You just set this up. So once you get
interject something here, Bob?
Go right ahead, Ron.
The important thing to consider when you're considering, you're managing your interlocks and protecting yourself against a VISWAR condition is that at this point in time, you're really not protecting your transmitter. Your transmitter has fold back. It's going to protect itself. You're protecting your infrastructure. And so that your combiner, your feed line, your antenna, they have a certain amount of reflected power that they can tolerate before you have imminent destruction and have a lot of explaining to do. So if you simply select a reflected power trip point that is well below the threshold of that antenna, you can avoid all sorts of problems and not have to worry about, what your transmitter is folding back to.
Yeah, because, and to add on it, to build on that, real world issue. This happened in New York City about 5 years ago. They had a major component failure in the antenna system. It happened to be caused by a careless workman who was up on the tower and crushed one of the feed lines to the main antenna that was up. And it started to cook away and developed an arc. because the line got crushed. So I guess the air, the air wasn't no longer holding air, so it filled up with water, and you know what happened? It started to arc, and it burned away until it completely, basically caught on fire, and none of the stations shut down. Now we've since replaced that. By the way, we've since replaced it was there with ours. Major project that we did with ERI in 2007, summer 2017. That won't happen again there. But previous to us being involved there, that happened, and the transmitters all folded back and stayed on the air. The thing is what happens with an arc is very simple. You have once the dielectric breakdown is achieved, and you develop that arc, you can run the power way, way, way down, and the arc is going to continue to be there. It doesn't take much power to sustain the arc. It takes a whole lot to get it to arc in the first place, and a lot of voltage breakdown, basically. That's what causes it. So foldback is not your friend. It's the transmitter manufacturer's friend. They're protecting their, their stuff from damage, but your transmission system can be woefully unprotected if you rely strictly on foldback to protect your system. So, every power meter that we make has a 3-strike VSWR protection. 3-strike meaning that you have to have a sustained condition in order for the interlock to open, or for it to open, give you an alarm condition. But we pride ourselves in the fact that we've been building these meters for a lot of years, and I get stories from customers who call and say, initially I was ticked off at you guys, but then when I figured out what was going on, I was very thankful. I had a guy down in Texas a few years ago who, bought one of our meters, put it in, and within about a week, took him off the air. And he initially was very angry at us until he sent they couldn't stay on. They they realized they had a high VISWAR condition. Had a guy climb the tower, and when the guy came down, he said, "Listen," he says, "this could have been a lot worse." He says, "You had a feeder that burned up." He says, "But the whole system could have burned up. It's just this one feeder that cooked." But I've seen worse than this. Where it just cooks away all weekend, and you don't know what's going on until you see fire coming off the tower. So he thanked me. He said, we put these meters in, and it covered the investment of the meter within a very, very short period of time. So. Look, this is a safety factor, and this is, it's not only do you want accurate power measurement, but you also want to protect the investment of the station. It's pretty important. So anyway, so those are some of the things we've been working on. This meter version will be available. I think we slate at the end of the month. We're going to start shipping these. So the only thing is, if you have a DPS 100D right now and you want to do this, you have to send us the meter back for recal. I mean, unfortunately, there's no way to do it. We can do it. We can add these new features for most meters, depending on the age of it. But you'd have to send it back for a recalibration and a firmware upgrade. We can't just do the firmware upgrade in the field. The calibration doesn't work the same way, so that would be required. Again, if your meters, if you got one and it's 8 or 10 years old, maybe it's time to think about replacing it anyway. But again, it's running and it's in service for you. I'm not telling you that you need to replace it, but if you want these new features, it's probably better to do that. So for a new installation, consider a new meter at that point. Or if you're going to take it out of service anyway, it's a good time to send it back to us for a recalibration. We can evaluate it and get it all up to speed for you. So that's where we are. I think I talked about everything I wanted to talk about today. So I'll open it up to I'll shut off the screen sharing here, and so that I can see everybody. And if anybody has questions, comments, anything like that, I'm here for as long as you guys want me to be.
Going back to your AES comments, I know that one of the reasons that the 3-conductor AES cable would be used is under the circumstances of AES 42 type 2, which is sort of related to AES 3, but that is full duplex, supplying synchronizations to multiple AES sources directly. and also potentially supplying power to them if they're not directly powered from other sources. So that's part of why that is there, and why I'm using it. So
Sure. Well, I'm not saying that you should never use it. I'm just saying that, like in this specific application that I was illustrating, the multiplex over AES, it just makes a lot more sense to use, use coaxial cable. But sure, there are other considerations if you're running power, and there are other considerations. What kind of data rates are you running at on AES 442? I'm just curious.
full 192 kilohertz.
Really?
When I can get away with it, at least I'm good to at least 100 feet of cable on that.
Well, listen, I think it largely depends on the source equipment and the terminations. In theory, the balance cable should work, but it just really doesn't have the bandwidth. I mean, that's been demonstrated. I wish, for some reason, the slide got missed. When I was editing this thing yesterday, I must have put that slide out that actually showed a bandwidth comparison between the two. It's like night and day. But
I'm sure the coax does much better, obviously. So.
Well, I mean, for that particular consideration, but there are other. You're right. I mean, you bring up the point that there are other considerations, and you have to do what you got to do, and for whatever the application is. I so okay. Any other questions? Anybody? Okay. Well, so again, I urge you to visit our website, which is again www.broadcast-devices.com. We have a Facebook presence. We have a YouTube presence that we just got started with, so we're putting stuff up on Facebook when we do there's a few things there that you might not find on YouTube quite yet. Demonstrations of things. I did a thing recently. Actually, one of the things I didn't talk about today is, believe it or not, we introduced a 67 kilohertz subcarrier generator, and people say, well, why in the world did you do that? Who's using subcarriers anymore? Well, we had a customer in upstate New York that actually asked us to build one for them because they needed to replace they had reading for the blind on one of their stations, and so we did a DSP based SCA generator, and I did a little video about that using an SDR actually as it's a software defined radio, one of the little cheap $30 dongles as a spectrum analyzer. It's kind of cool. You can use it to look at the baseband spectrum and whatnot. So that's up on Facebook. But that's the kind of stuff we're going to do. We're going to add a little, we do things here in the shop. They're not fancy, and they're maybe the production is not, you TV guys are probably laughing at me, but holding my camera phone, just demonstrating something here, standing at the bench, but do that kind of stuff once in a while. So, Barry, I see you turned your microphone on. Did you have something you wanted to say, or did you not know?
No, I didn't know. I could talk, say I enjoyed your presentation, Bob, and some things you said there were very interesting and informative for me. I got more questions to ask you.
Well, you know where to find me, so.
I do.
You want to ask him now? Go right ahead, fire away. I embarrass easily.
It's the folks there in Portland that need to take this time. I've got my time on Thursday.
Okay. All right. Okay, so I didn't realize that I could. There's a whole. Is there more people here that I? I see. There's some people that are on. They just are listening. I guess they don't have their video turned on and they're listening. So. All right. If there are no other questions or anything like that, I guess we're done. Unless you want me to hang out and show you anything, I guess I'm kind of talked out. So I want to thank everybody for spending the time. Hope the next time we do this, it'll be in person. I like Oregon. I really do. I enjoyed the last trip I was down there. I especially Medford, because that was the last stop on the tour, and I was able to go home after that. And the airport was right down the street from the hotel. It made it really easy. So again, I thank everybody for and Barry, call me sometime. You can ask away any question you want. I know sometimes it's tough to get me, but I'm here. I'm almost here every day now. So.
Okay. I'll be there. I'll be
All
there.
right.
Promise.
Okay.
Thank you very much, Bob.
Okay. You're welcome. Again, I appreciate the time that everybody spent with me. You have a great afternoon.
Thank you.
Take care.